Hello, discrete math fans. We'd like to offer an alternative formulation of the greatest common divisor. So first, let's give a definition to say that an integer d is called a linear combination of integers a and b if and only if there exist integers s and t such that as plus bt is equal to d. If you've studied linear algebra, it's kind of like that, but in linear algebra you sort of do it in a different way. All right, now here's the alternative formulation of the GCD, and this is called Basu's identity. And it says that for all integers a and b, and again, when we define the greatest common divisor, we have to have that a and b are not both 0. One of them can be 0, but not both. So if d is equal to GCD of a and b, then there exist integers s and t such that as plus bt is equal to d. Now we're going to prove Basu's identity. And this proof is another application of the well-ordering principle. The well-ordering principle, at least in this class, is not useful in and of itself. It is a useful theorem to help us prove other theorems. It's sort of like a super-duper lemma. So let's let a and b be integers, and they're not both 0, and assume that d is equal to GCD of a and b. Our goal is to find integers s and t so that as plus bt is equal to d. Let's define this set. It's the set of all x in the natural numbers such that x can be written as as plus bt for some integers s and t. Keep in mind, as we're working on this, s and t are allowed to be negative or 0. There's no restrictions on them, just that they have to be integers. Now, we'd like to apply the well-ordering principle on this set S, but if you think back to what the well-ordering principle says, the set S has to have a lower bound, and it has to be non-empty. Now, we know it has a lower bound because, well, it's only made up of natural numbers, so we could use 1 as a lower bound. Now we're going to show that it's non-empty. All right, so in case 1, if a is positive, then all we need to do is say 1 times a plus 0 times b. That's going to be an s. What if a is negative? Then we just need to do negative 1 times a plus 0 times b. That'll be an s. Okay, what if a is 0? Well, in that case, we know that b has to be non-zero because a and b are not both 0. So if b is positive, then we'll just do 0 times a plus 1 times b. That's an s. And if b is less than 0, then we'll do just like we did in case 2. We'll just say 0 times a plus negative 1 times b. That's an s. So no matter what case we're in, we've proved that s is non-empty. There's something that's in s. So the well-ordering principle tells us that s has a least element. And we're going to call that least element c. Now the definition of S tells us that c is equal to as plus bt for some integers s and t. So the real goal now is to show that this c that we just came up with, it's the same as the GCD. It's actually the case that c is equal to d. And the way we're going to prove that is we're going to show that d is smaller than c and c is smaller than d. When I say smaller, I mean less than or equal to. Okay, so first part of the proof, we're going to show that d is less than or equal to c. And the way we'll do that is to prove that d divides c. That will tell us that d is less than or equal to c. Now we know that d is the greatest common divisor of a and b. So if it's the greatest common divisor, then it is a common divisor, meaning that d divides a and d divides b. So that means we can say that a is equal to d times x and b is equal to d times y for some x and y in the integers. So now we'll take c equals as plus bt and rewrite the a and the b as dx and dy, and then we factor out the d. And therefore, d divides c. Both d and c are positive, so that must mean that d is less than or equal to c. Let's go the other way now. let's prove that C is less than or equal to D. So what we'll do is we'll show that C is a divisor of both A and B, and then since D is the greatest common divisor of A and B, we'll have that C is less than or equal to D. So if we use the quotient remainder theorem and take A and divide by C, we'll get A is equal to CQ plus R, where Q and R are integers, and R is between 0 and C, not including C. Okay, we're trying to show here that C is a divisor of A, so what we really want to do is show that R is 0. Now we'll rewrite this and we'll get R is equal to A minus CQ. And we also know that C is equal to AS plus BT. So let's plug that in. So we get R is equal to A times CQ. We plug in the C and then do a little bit of algebra, and we end up with R is equal to A times 1 minus SQ plus B times negative TQ. I'm not going to walk through all the algebra. That's not all that important. What is important is that R is a linear combination of A and B. Now, if R were bigger than 0, then we'd have that R is in the set S that we created. And that would make R a smaller element of S than C, and that would contradict the fact that C is in fact the smallest element of S. So that means that R has to be equal to 0. So A is equal to CQ. That tells us that C divides A. An almost identical argument, you can use mutatis mutandis to describe this, will establish that C divides B. And so therefore, we'll say that C divides A and C divides B, and so C is a common divisor of A and B. And we know that D is the greatest common divisor, so C is less than or equal to D. Okay, that's all for now.